Welcome, my name is Fabian and I'm going to talk about how you create a vSphere infrastructure design to support a Horizon implementation. When we designed the vSphere environment to support our Horizon environment, we need to differentiate. Do we size it for our resource block, so for our desktop workload, published application workload, or do we size it for or design it for the management block workload, which means all kind of the management components in our environment? Typically within vSphere we utilize the features of vSphere HA, high availability, DRs, the distributed resource scheduler, and for sure there is this option to use distributed power management as well that makes sure that workload is migrated, physical servers are shut down and powered on again after a certain amount of time. Important, how does that look from a licensing perspective? Horizon, we always have license for vSphere for desktop, which means we can utilize as much vSphere components as we need to let our workload for management, so the Horizon management and the end user workload running. Okay, so we do not really need to care about the vSphere licensing topic that much. So one thing we need to consider here as well, for each cluster we create, we need to define certain configuration items. We need to define certain configuration topics. And we need to know that, for example, if we create a pool, a desktop pool in Horizon, we cannot span that across multiple clusters. So we only have one desktop pool that we can add to a certain cluster, which means the workload within this managed desktop pool is only deployed on a single cluster within our environment. And those are kind of constraints or characteristics we need to know when we create, design, build the proper vSphere solution for our environment. In general, we need to consider the DRs and HA settings in all scenarios. Meaning if we design it for a workload cluster or for our management cluster, we typically want to enable vSphere high availability. What does it mean? The failuring of an ESXi host is detected and the failed virtual machines are restarted on the remaining hosts in this cluster. Since we have built our connection servers in a way that they are redundant, that the failure is also detected by the load balancer and the connections are redirected to the other connection server, we really increase the availability of our virtual desktop servers tremendously by also enabling vSphere HA. Since then, the connection server is, after a failure, powered back on a different ESXi host and then joins back to our active connection server set if it's properly configured within the load balancer. What else can we configure here? We can say, okay, we want to check the state of a virtual machine in the HA cluster. So if a virtual desktop is kind of freezing, is kind of having a blue screen, which might happen in a Windows-based VDI environment, the VM protection mode of HA detects, okay, no VMware Tools heartbeat is occurring, no network and disk I/O occurs. I reset the virtual machine and bring it back to life after reboot. Remember, if the reset occurs, a screenshot of the console session of this VM is stored on the data store of this virtual machine. VM component protection is also a configuration item within the physical design. If we use for our workload cluster any kind of a stretch cluster component, if we use block-based storage, it might be that we want to also react not just to host failures or VM failures, but also to failures in the storage stack. Failures for permanent device losses or all path down scenarios where we can also act with our vSphere HA cluster. Please consult the documentation of your storage vendor to get the proper configuration item for those HA options. When we talk about vSphere DRS, that's the distributed resource scheduler. The distributed resource scheduler makes sure that our bunch of ESXi hosts can be seen as a logical pool. In certain scenarios, DRS can kick in and say, okay, on this ESXi host, we have a CPU resource contention and migrates virtual machines from one ESXi host to another to ensure that the service for the end user is in the end the best possible way. So we typically keep the DRS cluster fully automated and typically don't enable the power management feature so that ESXi hosts are powered down and started up again once a certain workload is observed. What we also need to discuss is the EVC mode, the enhanced vMotion compatibility mode. If we have older ESXi hosts with older CPU generations and newer ESXi hosts with newer CPU generations, to make a more easy migration possible, we can make use of the EVC mode and for sure the HA isolation response. So what should happen if an ESXi host is isolated? Should it shut down the virtual desktops or virtual machines or keep them running? Those are characteristics that needs to be aligned to the physical environment within the customer's environment. Typically, what we need when we design a vSphere cluster, we talked about the configuration of DRS and HA, but what we need when we design the vSphere cluster is we need the capacity requirements. The capacity requirements can either be calculated by using an allocation-based model or a demand-based model. We will talk more about that later. We need to figure out how many host failures we want to tolerate. Do we want to tolerate only one host failure? Do we want to tolerate 2 host failures, or a number of host failures that are built into a rack or a data center? Those are things we need to consider, or those are things we have captured during the assessment phase, during the conceptual design phase. We want to have redundancy. We need to figure out which storage we are using. We talk more about storage design in a different section, and we might create the solution in a way that we can easily add new hosts to our design, which means we should probably not go right from the beginning into any kind of configuration maximum for our clusters. When we talk about doing a physical design of our management block, we need to understand which components do we place on the cluster underneath our management block. We need to understand which services do we need, how many instances do we need of the certain service. We need to specify, and since we're now in the physical design phase, we need to specify a host name, a DNS name, an IP address, network characteristic, probably firewall rules required to create a proper connectivity. We need to know which operating system is used underneath. Is it Windows or is it a virtual appliance? Remember, since we have the vSphere for Desktop license, we can use as many vSphere hosts as we wish to host our VDI platform relevant components. But we still need to license probably the guest operating systems running on top of our management cluster. So we need the proper Windows license. We probably need the proper SQL license. If VMware delivers a virtual appliance, we do not care about the license within the virtual appliance. That is something that is part of the solution in the end. So what we typically do, or what we can do for our management cluster, we figure out which components do we need. We give it the IP address, the host name, like you see on the screen. We size the components properly. For connection servers, for vCenter server, we talked about the proper sizing already. We need to know how many vCPUs do we need, how many gigabyte memory do we need, how much disk space do we need, and we need to put that into an Excel list and get some kind of summary, like in our example where we placed multiple vCenters, multiple connection servers, multiple app volume manager, also some domain controller on the management block to create some kind of solution independence from other third-party services in the environment. And we figured out that we will need around 60 vCPUs and 176 gigabyte of memory for our management workload. Again, during the conceptual phase, we might have figured out that those elements might change, that there are projects in plan, that more users should come to the environment, that more access opportunities should be created to access the environment. that a certain growth is expected. Those are all things we should consider right in the beginning here as well, since that impacts our physical design, or we should create our management cluster in a way that we can scale it out or scale it up easily. When we talk about an allocation-based capacity model, we can assume a certain amount of vCPU per core ratio that should fit for our need. Yeah. So if we have a consolidation rate of 3 vCPUs per 1 core, we need around 20 cores to fulfill our required capacity for CPU. And since we have around 176 gigabyte of memory required, and we have some overhead for certain processes, vMotion, some free room for certain growth, we would recommend to have 196 gigabyte of memory installed in the ESXi server. But we want to have a scenario where one host can failure, which means we need 2 servers that have 20 cores each and 196 gigabyte of memory to fulfill all of our requirements that we have at this point in time. And remember, we know, or we need to always get back into the conceptual design and figure out if there was any kind of change, if there was any kind of planning happening. We need to, we just assumed at this point in time that the ratio of 3 vCPUs per 1 core on the management cluster is good enough. This assumption must be controlled over the time to make sure that we still have enough resources in case of a failover right here. So the management cluster has been sized in a more allocation-based model, where we use the allocated resources we give to our virtual components and apply them to any kind of physical resource characteristic. When we talk about the workload cluster on our resource block, it is the best practice to use real data from real desktops that exist in the environment. That can be either data that has been extracted from physical desktops that are already used by the end user in the company. That can be data extracted from any kind of user acceptance tests, from any kind of pilots that run or that were used for certain realistic use cases in the environment. And the typical outcome of such an analysis is something like you can see on the screen. The average number of CPUs that was figured out during the assessment, the average CPU utilization, the peak average CPU utilization, the memory utilization, the peak memory utilization, the disk IOPS required for reads, the disk IOPS required or used for writes, and any kind of network utilization and storage latency. So we need all of those information because this workload characteristic has an impact on the sizing of our cluster. Besides that, we need to figure out once again, how many host failures do we want to tolerate? How many concurrent users or desktops will we have per use case? Which types of desktops do we have? Which Windows version will it be? How do we deal with the usage of physical GPUs in our environment? We need to get all those information together, and therefore, based on those information, create a physical cluster design with physical hardware in our target environment. So how can this look like? Let's take the example that we have certain requirements defined and already written down, figured out in the conceptual phase of our design. We want to tolerate the failure of one ESXi host. We have around 2,000 concurrent users, and every user only has one desktop. At the same time, the cluster we are sizing is used for the use case of the task worker, which requires 2 virtual CPUs and 4 GB of memory. So, since we already made an assessment of this use case, we know that the peak CPU utilization for this user per vCPU was 250 MHz. So, let's come back to the constraints. Our customer already has bought 10 servers with 2 CPUs, where each CPU has 16 cores and 2600 MHz. And every server has 512 GB of memory installed, which means we already have a certain physical server set available not sized for the requirements, but bought upfront. Very realistic scenario. So the question is, how many physical servers would we need to fulfill those requirements? So based on the fact that we want to design for the CPU peak, we can work with a consolidation ratio of 10:1. Why? The peak is 250 megahertz. 10 times 250 megahertz, we end up at around 2,500 megahertz that we require per core when we use this consolidation ratio. This is quite something we can work with. Okay, so we would need usable physical cores for our environment, where we have 2,000 desktops, of 400. So we need 400 physical cores, which aligned to the constraint or to the already bought server means that we require 13 servers, where we add this n+1 characteristic, which means we would need a total of 14 servers to deal with the resources that we have figured out during the assessment phase. And now this is really, really important, because now we have probably a really small headroom available for our environment. Yeah, so probably the better approach would be to use 15 servers. Yeah, to figure out that probably maybe there will be some change in the operating system. We migrate to a new operating system that will require more CPU cycles. We might migrate to a new distribution methods for software, to a new antivirus solution that require more CPU cycles, that will at the same time change the vCPU to core ratio in our environment and might suddenly require much more physical servers than we have planned up front. So that is something we definitely need to iteratively analyze all of the time. We can use vRealize operations for that, to always have a good capacity planning mechanism in place. Okay, so we can see that the constraints we have identified during the conceptual phase, that 10 servers have already been bought, might most probably lead to a certain unsatisfied user base, since we might not be able to handle the workload that has been identified up front, and we need to escalate the topic directly to the project sponsor, to the specific stakeholders that help us to solve the problem in the end.